Welcome back. Over the past series of videos, we've been putting together our vision transformer architecture. But let's not stop there. We've replicated the architecture itself. It's now time to train it to see how it goes on our food vision mini data. Now you might have already tried this because we've trained a fair few pytorch models over the last few sections. But if not, let's now do it together. So we'll go section 9, setting up training code for our custom ViT. So we'll write down here, we've replicated the ViT architecture. Now let's see how it performs on our food vision mini data. Because that's the whole purpose of Milestone Project 2, right? Is not only to replicate the paper, but to see if one of these state-of-the-art computer vision architectures works well on our own custom data. So the first thing we have to do is create a loss function or an optimizer. So creating an optimizer. And how might we find what optimizer to use? Well, of course, we could use the optimizers that we've been using in the past, such as SGD, stochastic gradient descent, or the Atom optimizer. But in light of replicating the paper, how about we do a little search and see what the ViT paper used as their optimizer? So I'll just create a code cell here. So if we go here and look for optimizer. Okay, additional analysis. ResNets are typically trained with SGD, so that's stochastic gradient descent, which we can find in torch optim SGD, which is part of the torch.optim package. Beautiful. And we see there's a lot of different algorithms here for PyTorch optimizers. Recall that a machine learning research paper will often use a pre-existing optimizer introduced in another research paper, and that if the optimizer is quite common, chances are it's within the PyTorch library. So there's an Atom W optimizer, which is a variant of Atom. And then if we come down, we have SGD, which is mentioned in the paper here. And our use of Atom as optimizer is quite unconventional. Okay. Here we show the experiments that motivated this choice. So that's hinting that they use the Atom optimizer as their optimization function. So what do we have here? Results are presented in table 7. Atom pre-training outperforms SGD pre-training on most data sets on average. Beautiful. This justifies the choice of Atom as the optimizer used to pre-train ResNets on JFT. Well, that's not really for the vision transformer. How about we look up training, and this is from section 4, I believe, of the paper, setup. So there we've got the different data sets. You might have already read through this. And then we've got model variants. We've seen that before. Now we've got training and fine tuning, which is exactly where we're up to. So we train all models, including ResNets, so all vision transformers, as well as the ResNets that they trained, using Atom. Beautiful. So that's the Atom optimizer, with beta 1 equals 0.9 and beta 2 equals 0.999. Well, where do we get those values from? We'll look at that in a minute. And then a batch size of 4096. So we're not using a batch size that large because we don't potentially have the memory to do so. And in fact, we only have a total of 250 or so images in our training data set. So we don't actually even need a batch size that big. So let's go back, keep reading, and apply a height weight decay of 0.1, which we found to be useful for transfer of all models. Okay, well, let's look up PyTorch's implementation of Atom and see what we can find. Atom. Oh, there we go. So Atom parameters, learning rate, we've seen that before. Well, this is the model parameters that we want to optimize. And here's the betas. 0.9 and 0.999. If we go back into the paper, beta 1 equals 0.9, beta 2 equals 0.999. Remember how I said optimizers, or if a function has made it into PyTorch's standard library, it generally uses pretty good values by default? Well, this is one of those examples, because the beta values here are exactly what the paper used. So if we scroll down, what do we have? We have betas, coefficients used for computing running averages of gradients and its square. So default is 0.9 for beta 1 and 0.999 for beta 2. And then we've got weight decay here as well. So let's look up here. What have we got? A high weight decay of 0.1. What's the default weight decay? It's 0. Well, we could set this to 0.1. Now, if we wanted to find out what is weight decay, let's have a look. Weight decay is a regularization technique. Now, what is regularization? Let's write this down. Create an optimizer. We've got a few things going on here. The paper states it uses the atom optimizer, and we have, that is in section 4, training and fine tuning, I believe the section is called. Training and fine tuning with B1, so I'm just using, oh, actually I could do the math version. So B1, so beta 1, value of 0.9, which is the default, and B2 value of 0.999 defaults, and a weight decay of 0.1. And weight decay is equal to, let's go back to here. What is weight decay? We've got many more resources here, but I'm just going to use the top one. This sounds pretty good. Weight decay is a regularization technique by adding a small penalty, usually the L2 norm of the weights, all of the weights of the model, to the loss function. So we know that weight decay is a regularization technique. And what is a regularization technique? Regularization technique equals prevents overfitting. So my understanding of weight decay from this is that it's going to reduce the weights in some way. If the weights get too large, weight decay is going to step in. It's only going to be a small amount, 0.1. And because it's a regularization technique, it's going to prevent our model's weights from getting too large and hopefully prevent overfitting. So with that being said, let's implement the atom optimizer. We could copy this, or we could just go optimizer equals torch.optim.atom, and we want to optimize the ViT model .parameters. I'll just show you what the ViT model is. ViT. This is our ViT that we created before. So a lot of layers there. Look at all that. We built that. We built all of those layers. So we'll comment that out. Optimizer equals ViT.parameters. We'll set the LR. What's the LR? The learning rate. Do we have that in table 3, which says a lot of different hyperparameters? So we're building this one, ViT base 16, and we have a learning rate of 10 to the negative 3. Wonderful. Now there's a few terms here, learning rate decay, and I think learning rate warm-up. You might want to look into those. That's another part of replicating the training. We're going to stick it with as simple a recipe as possible to begin with. So LR equals 10 to the power of negative 3, or 10e negative 3, or 1e, actually I think that's better to say, 1e negative 3, or 0.001. So 1e negative 3. Beautiful. And then what do we have? Well, we have betas. We don't actually have to set this because by default in PyTorch it is 0.9 and 0.999. So we'll just put that there anyway. And then the weight decay, which is by default 0, we want to actually put that to 0.1. Equals 0.1. Beautiful. And there is our optimizer. So how about a loss function? Now if we search the paper for loss, well, what about loss function? No results. What about criterion, which is another word for loss function? Nothing. What about cross entropy? Well, this is one of those things where the paper, I guess it kind of assumes that we know that it's using cross entropy loss function because we're working with multi-class classification. So it doesn't actually mention it if we search for loss function, as you saw. So I'm going to write this down. The ViT paper doesn't actually mention what loss function they used. So since it's a multi-class classification problem, and in fact, if you read the paper and find that they do mention the loss function, please let me know. But from my research, I couldn't find it. We'll use the torch nn.cross entropy loss because that's the multi-class classification loss. So loss function equals torch.nn cross entropy loss. Beautiful. So there we go. We have created an optimizer and a loss function. And now I believe we're up to, let's go, 9.3 is training our ViT model. So we have now, this is super, super exciting. We've got all of the pieces of the puzzle to train a model. We've got our architecture, we've got our optimizer, we've got our loss function, and we've got from going modular, import, we want engine. And then if we go results equals engine dot train, what does our train function take? Should we get a doc string here? Missing 7 required positional arguments. If we put in the model, the training data loader, the test data loader, the optimizer, the loss function, the number of epochs, let's say 10, and the device we want it to train on, of course, the GPU if we have access to one. We should, because we've got runtime type, GPU, wonderful. And then we can check it here, NVIDIA SMI. So everything is ready to go. So that is my challenge to you. Try to fill in the training code here and see what happens when you train our first custom ViT model. Give it a shot and we'll do it together in the next video.